We're now receiving a video downlink from the X-band synthetic aperture radar in Discovery's cargo bay as Discovery prepares to pass over the southern tip of Japan. And this view is from the X-band synthetic aperture radar measurements as it is made above the southern tip of Japan. Discovery just now above southern Japan on a track that will shortly take it off the eastern coast of Japan above the Pacific.
Well, let me start from the top again. Good morning, I'm Tom Jones, the payload commander on Space Shuttle Endeavour on the second flight of the Space Radar Lab on mission STS-68. We're here on the flight deck winding up some business on the blue shift. We've conducted a whole 12 hours of Earth observations on this shift, and my red shift colleagues are ready to come on duty in just a few minutes. We have a few minutes here at the end of the shift where I'd like to tell you about our activities on board, tell you about the major components of the Space Radar Laboratory, talk about our science goals for the week's activities, and tell you about some of the examples of global change that we look forward to sharing with the people and the scientists back on Earth. This Space Radar Lab 2 is part of NASA's mission to Planet Earth. That's a program that NASA's conducting to look at Earth's life, land, water, the air around the planet, and all the interactions of those components. We're trying to understand Earth as a single complex system so that we can get a handle on the real numbers behind the changes our globe is experiencing. Now, the Space Radar Lab goal as a part of Mission to Planet Earth is to look for those hard numbers on Earth's changes, both man-made and natural, and try to bring those back to Earth so we can understand how we're affecting the planet and how we have to cope with those changes. Now, to do that, we have a payload bay full of sophisticated instruments that last flew in April on STS-69, and I'd like to tell you a bit about those, and I've got a little video segment here to show you those components. The first component we have on board Space Radar Lab is a state-of-the-art imaging radar, and we're going to show you here in this view as we come down from the overhead windows our Cersei XR radar out in the payload bay. The other component of SRL is the MAPS air pollution sensor, and in this view of the payload bay you can see the large radar array stretching from about the forward end of the bay all the way back to the tail. It's labeled JPL, that's the Cersei XR instrument. The Langley Research Center logo is on the MAPS instrument just to the right of the screen, to the left of the Canadian arm. And the small segment of antenna labeled XR is the German-built component of Space Radar Lab. Now, these sensors in the cargo bay aren't very useful unless we have the crew here on board to operate them. For the imaging radar part of the mission, the crew has an essential role to play. There's a huge amount of data coming down from the instrument out there as it images the Earth's surface, and those images have to be transferred to the ground. We don't have enough communications link on board to transfer them all in real time. So the first role of the crew is to handle the data coming back from the radar, and we do that by changing out our data tapes on board. We have about 207 data tapes on board. Each of them holds 50 gigabytes of data, and we've gotten very good at practicing changing out those tapes. We hope to bring back about 52 terabits of data, something like 20,000 encyclopedia volumes of information by the time we're finished. The second part of the crew's role is to handle the photography that supports the science investigations around the world. In many regions of the world, we don't have scientific teams on the ground to validate the results from the radar or from the MAPS pollution sensor. And so we are the ground truth. Our photography, some 14,000 still photo frames, is going to be used to provide the environmental conditions over those targets in remote areas of the globe where we don't have independent verification. And the last thing we're doing, and probably the most important role that the crew's playing on this mission, is to point the payload bay instruments at the required targets. And to do that, we're conducting a succession of maneuvers, about 409 of them during the mission. And that's about 25,000 computer keystrokes to tell Endeavour's computers how to orient the payload bay so as to get the optimum data coming back down to the ground. Now, the radar out in the cargo bay, Cersei XR, is a synthetic aperture radar, and it paints a picture of the Earth's surface through darkness and clouds and can thus operate around the clock all the way around our orbits every 90 minutes around the globe. The MAPS pollution sensor is an infrared spectrometer, and it measures the amount of heat radiation coming up from the ground and converts that into information on how much carbon monoxide is lying just beneath the space shuttle as we go around the planet. And over a couple of days, we can construct a map of pollution sources and the way the CO is moving around the world on a day-to-day basis. And this is a very good comparison with information we got last spring and on 2 previous flights of MAPS. And this is just the key to our whole mission, just looking for changes around the world. We're looking for changes since last April's STS-69 mission, Space Radar Lab 1. We're looking for changes in the previous MAPS data over the last 10 years. And these 2 flights and other flights in NASA's mission to planet Earth will show the ability to monitor the Earth as a global system on a permanent basis. We're looking for changes like ecology changes around the world, climate changes, and some dramatic changes on the surface that we're more familiar with, like volcanoes and storm systems, for example. In the area of ecology, we're looking at clearing and deforestation around the world, looking at the tropical and northern forests of the world to see the rate at which we're destroying the forests and the rate at which they're renewing themselves, so we can really quantify that important phenomenon in the ecosystem. We've already seen a lot of forest fires over in Asia and in Australia, some at night over Africa and in South America as well. And our data, when we come back, will give us the rates of forest change around the world. In terms of pollution, we're looking for the way that carbon monoxide drifts around the world from its sources like forest fires, and that will help us track seasonal pollution and also tell us what the most important sources are in various seasons, whether it's natural burning from forest fires or industrial sources like cities and automobiles. We're looking for climate change by looking at the geology around the world for traces in the geologic past of rainier and drier periods in the Earth's deserts and the valleys that show alluvial fan erosion. Those are very key points to investigate for looking back into the Earth's climatic past. And of course, some of the most dramatic things we're seeing in terms of change have been the volcanic eruptions up in Kamchatka yesterday and the day before. And we've also been looking at several storm systems down in the Southern Ocean that we can track on a day-to-day basis. And there are targets for both the radar and some of the MAPS instruments because those storm systems can distribute pollution around the world. We have a busy week ahead of us here on Space Radar Lab. We've got a lot of work to do in terms of maneuvering, changing the tapes, and most important for us on a daily basis is taking all those still photos from the aft windows. It keeps us constantly busy when there's a daylight pass going on. That's not surprising. The Earth is a very complex system. It takes a lot of study to understand it, and only a future permanent platform or a suite of instruments in orbit is going to be able to do that on a permanent basis. And we hope that by flying this test bed, we'll prove that that principle will in fact work. We're getting a taste of some of the exciting results that we're anticipating here in orbit with our own eyes. And it's going to be an exciting look at the data when we get back to the ground with those 207 data tapes and really see in full fidelity what the SAR XR and MAP sensors have brought back. But we can see the changes here, and we're going to try to share them with you in the coming week. We look forward with you to learning more about the Earth this week on Space Radar Lab 2 and learning some more about our amazing planet that we live on. And we are very proud to be up here exploring it on behalf of our country and the other scientists on the team around the world.
How'd that go? Loud and clear, Bakes, with COPAO thought. We're all happy. You look good up there. All right, great.
Synthetic aperture radar can see through cloud cover and take real-time imaging of the Earth's surface. Again, Endeavor's tracking northeast across the Yucatan Peninsula. While it's dark on the ground, Endeavor's still in darkness. The radar sees through darkness and clouds and any other kind of interference, providing detailed images of the Earth's surface. This of the Chilchuca area of Mexico, of the Yucatan Peninsula. The objective data take are to develop models for the wetland vegetation and area in this region.
Okay, well, we'll give it another try later when we can close out all the applications, and maybe we'll have enough memory then to bring it up.
Copy. Joining us on the deck of Space Shuttle Endeavour, more than 120 miles above the Earth, is astronaut Jeff Weissoff. Jeff, thanks for joining us, first of all. I've been listening to you all day tell ground controllers what the Earth looks like as you fly over. In fact, several hours ago, you were describing the east coast of the United States, just about sunrise. What does it look like from your vantage point compared to how it looks to us when we fly over the United States in an airplane?
Well, John, obviously we have a much bigger view of the whole thing, and for me in particular, the East Coast, having grown up in Norfolk, Virginia, it's great to fly over the Chesapeake Bay area. It was clear this morning, and we could see all the way from the Norfolk area up through about the Delaware Bay area. And you get a feeling for just how much difference there is in the kind of land contours. You can see the Appalachian Mountains off in the distance, and you can see sun glint in the water at certain sun angles, which will allow you to actually see water patterns. And that's one of the things that the radar is going to be interested in looking at, is to try to understand eddy currents and things of that sort in the water. And we'll be taking photos, and they'll be trying to compare that to what the radar takes.
How much time do you get to look out the window? And how much do you use cameras to take still pictures and movies as you look out the window?
Taking pictures is actually a very important part of what we're trying to do. What this mission really is about is trying to verify that this radar can measure things on the ground that we normally have to send out ground teams to measure, things like the amount of water in the soil, vegetation, deforestation, things of that sort. What we're trying to do with these missions with the radar is to send ground teams out, take pictures with the radar, find out that if we can interpret the pictures in the radar to give us the same types of measurements that we get from the ground teams, all those expensive ground teams will no longer be needed, and we'll be able to fly a radar long-term in space to take these measurements. So what we do with the pictures out the window is we act as the ground truth for areas where we can't deploy ground teams. For example, in very remote areas of the world where we can't send ground teams, we can take photos that they can compare to what they get with the radar to make sure that their interpretations are correct.
Yeah, I remember